Right, let's go through these end of topic questions in electricity. I would rather go through them with you because a lot of them are pretty tricky. So just looking at my answers might not be decent enough, and my working out isn't showing the best, to be honest. So I'm going to try and be as quick as possible. 1A, what flows in the direction indicated by the arrow here? So this was the wee arrow that was drawn on your page, and it's going away from the positive towards the negative, so it must be the conventional current. So I just wrote current down for my answer. B, mark on with an arrow to show the direction in which the charged particles flow, so that's the electrons, and we know they go from negative to positive, so we know this one here is what is really happening, but we mark on conventional current the other way around. C, what name is given? Oh, electrons. And then D, the current in the larger resistor is 0.6 amps. So see, whenever I'm reading questions like this, I will always mark things on the diagram. Makes it way easier. So the current in the larger resistor is 0.6 amps. State the size of the current in the smaller resistor. Well, these are connected in series. So if there's 0.6 amps going into this one, there's 0.6 amps going into the 10 ohm one as well. Then E, show that the electrical charge delivered by the battery in 1 minute is 36 coulombs. If you ever get a show that question, it means your answer should be what they are asking you to show. So your answer should end up with charge equals 36 coulombs. So we just use Q equals IT for that. The current was 0.6, and 1 minute we need to change into seconds, so that's why that's 60 in there to get 36. Okay, should have warned you, my answers are a wee bit all over the place here. Sorry. So resistors of 20 ohm and 10 ohm are connected in series across a battery. So as I've been reading that, I've sketched a wee diagram there. The current in the larger resistor is 0.6. Show that the battery voltage is 18 volts. Well, with my little sketch, I've drawn on the two resistors, and I've marked the current going in here. So we know current is going to be the same the whole way through here because they are connected in series. This current here is going to be part of like V equals IR, so with this voltage and the total resistance, because these are connected in series, our total resistance is going to be 20 plus 10, so it's 30. So that's the resistance that we use in V equals IR. Voltage from the power supply, total resistance of the circuit gives you the current that's drawn from the power supply. So there's my numbers put in, 18 volts. Right, 3. Two identical resistors are connected in parallel across a battery. Their combined resistance is 12 ohms. What's the resistance of each resistor? Well, I get my working out not great here, but I've just sketched it. Two resistors connected in parallel, and we know combined these have a total resistance of 12 ohms. Well, if you remember the sneaky wee rule, if you've got two resistors the same as each other in parallel, the total resistance is just half of one of the resistors. So that must mean each of these is 24 ohms. And then B, very similar, but this time in series. Yeah. So a different pair of identical resistors are connected in series across a battery. Their combined resistance is also 12. What's the resistance of each resistor? Well, the rule for combining resistors in series is that you just add them. So if these two in series add up to give us 12, each one must be 6 ohms. Okay, question 4 then. I've tried to position this. Same advice here. As you're reading it, start to mark things onto your circuit. So I'll talk you through the way I would have done that before we start looking at any of the answers. So in these two diagrams here, the lamps are identical. So that means the resistance of each of them is going to be the same. And each has an internal resistance of 6 ohms. So the first thing I would have done there would be to mark on 6 ohms, 6 ohms, 6 ohms, 6 ohms. Okay. Each cell in the battery can supply a voltage of 1.5 volts. Well, we've got two cells here, each with 1.5 volts, so that's going to be 3 volts. And then same in this one, each cell 1.5 volts, we've got two of them, so it's 3 volts. For each circuit, find the reading which will be shown on the 4 meters. So we've got ammeters and voltmeters here. Well, we've already kind of done a couple of them. So V1 is the voltage across this power supply, so that's the 3 volts that we've already marked on. V2 in this one is this voltmeter here. Now remember, in these circuits, we sort of act as if the ammeters and voltmeters aren't there. They're like we act as if they're not in the circuit. So if I cover those all up, then all we have here is a power supply with two bulbs in parallel with each other. And the rule for voltage in parallel is that it's the same across each parallel branch. So that's why that one is 3 volts. Other way you can think about it, if you do the wee trick where you follow the path of the current. So if you're the electrons, you're traveling along here, you pick up 3 volts. Remember, you arrive back there once you've done your loop of the circuit. You arrive back with 0, so you have to get rid of all 3. Well, if you're one of the electrons that goes through this one, this is the only thing that you visit, so you have to give all 3 volts to it. And then same if you're the one that goes down to the bottom one, it's the only thing you visit, so you have to give all 3 volts to that. Then A1, to get it, we needed to use it's the current that's being drawn from the power supply. So remember, for it, it's the voltage of the power supply, and we use the total resistance of the circuit. So this is my working out for this. So the total resistance, we've got 2 6 ohm resistors. Well, I know they're bulbs, but 2 6 ohms in parallel with each other. So combine those, we get 3 ohms. And then I can use I equals V over R. So the voltage of the power supply is 3. Total resistance of the circuit is 3. So I get 1 amp going here. And then to get A2, I can just use my rule for how, well, there's a couple of ways we could do it. But the way I would do it is I just use the rule for current in circuits. So remember, current splits across parallel branches. Because the resistance of each of these branches is the same, then it's going to split equally. So if we have 1 amp coming down here, we're going to have half an amp going here and half an amp going there. So A2, 0.5 amps. The other way we could have done that would have been to use V equals IR. This time though, the voltage would be the voltage across the bulb, which is still 3, and the resistance of the bulb, which was 6, and that would give us 0.5 again. Then circuit B. So again, we've already marked all this on. So V1 is the voltage across the power supply, so that's the 3 volts. V2 is across just this one bulb here. So we need to think, what's our rule for voltage in series? So remember, ammeters and voltmeters react as if they're not there. So we've got our 3 volts, and the electrons come along, pick up the 3 volts, and then they deliver all 3 to the things that they visit in the circuit. So this 3 volts is going to get split across each bulb. So that's why that one is 1.5 volts, because it's just half of 3. A1 is the current from the power supply. So again, we're going to use the voltage of the power supply and the total resistance of the circuit. So this time our total resistance is going to be these two added together to give us the 12. Then I can do that in I equals V over R. Voltage of the power supply is 3, total resistance is 12, so 0.25 amps. And then because it's series, A2 is just going to be exactly the same. Whatever current you have traveling down here, still going to be the same amount of current there. Right, question 5 then. 4 identical resistors. So this one here, sorry, I should have said this question here, I think is way harder than anything you would ever get in an exam. So if you can get this, top notch. Yeah, way harder. And actually, I'm pretty sure for part C and D, you're not expected to be able to do this for GCSE. We're going to go over it anyway because we're experts. So 4 identical resistors are arranged as shown here. So each of these resistors has the exact same resistance. So whatever these are, this one is as well. So basically what we've got is 3 resistors in parallel with each other, and then that parallel combination is in series with this wee one here. Okay, so as I've been reading this, I will have just started filling things in. The current entering at X is 3 milliamps. So we've got 3 milliamps going in here. And the voltage between X and Y is 12 millivolts. So the total voltage between this point and this point is 12 millivolts. So it's like you've got a 12 volt supply up at the top, and then this is all just connected here. So these 12 millivolts are going to get split across these two things which are in series with each other. Right, calculate the total resistance between X and Y. To do that, you're just using the total voltage and the current for that. Right, I can't actually remember where it was. I had to pause there because people came in. Hi, Mr. Reed. What was it? The total resistance between X and Y, yeah. Just use the total voltage 12 and the current, the total current. So the total current here is 3 amps. So we get 4 ohms. So that means all of these combined gives us a total resistance of 4 ohms. Now, next we want the current in each resistor. So we've got 3 milliamps coming in here, and we know current splits in across things in parallel. Well, we were told at the start of this that each resistor has the same resistance. So that means the 3 amps are going to, or 3 milliamps, sorry, I keep leaving out the milli, are going to split equally. So we're going to have 1 milliamp, 1 milliamp, and 1 milliamp. So the way I've just written that in my answer is the ones that are in parallel are getting 1 milliamp each. Then that's all going to combine again to give us 3 milliamps for the wee one on its own. Sorry, there. Now, see, this is the bit that I am so sure you would never be expected to do. The voltage across each resistor, because they're asking you to do that before you know the resistance. If you knew the resistance, you could just do V equals IR, but to get the voltage across each resistor, we can use our wee ratio rule. So if our total voltage here is 12 millivolts, if we think about the paths of the electrons, so they're coming in here, say you're one of the electrons that goes up here and here, you're only visiting two things, so this 12 has to be split across the two things. Now the way it splits is the ratio of the resistances. So let's think about that. If we have 3 equal resistors in parallel with each other, then the combined resistance is a third of one of the original resistors. Do you remember that? So that means that our voltage has to split across the things that are in series in the ratio of their resistances. I wonder, did I show good working out for this? No, I didn't. It has to split in a way where the two numbers have to add up to give us 12, and one of those has to be a third of the other one, because the total resistance here is going to be a third of this resistance here. So that's why it's 3 and 9, because those two numbers add up to give me 12. Look, I've written volt as well instead of millivolts. They add up to give me 12, and the resistance here is a third of this resistance. Even though I don't know the values of the resistances yet, I just know the ratio of them. This one is 3 times this one because these are connected in parallel. Okay. And then part D, the resistance of each resistor. Well, now we know the voltage across each one and we know the current that's going through them. So if I do it just for this one, I can use R equals V over I. So voltage 3 millivolts, current 1 milliamp. It's going to get me 3 ohms. And then just to check, I'll do it for this individual one. So I said the voltage across this individual one was 9 volts and the current going through it was 3 millivolts. I still get 3 ohms. So that's good, that I'm getting the same thing. Okay, I haven't quite got those finished here this morning. We still have to do 6 and 7. I will record that later for you. Okay, bye.